It flows from a source to a destination. Okay? And a lot of times when we're talking about this energy, we can measure it in terms of thermal energy. We can measure it in terms of a temperature change. In a chemical reaction, we have energy that holds bonds together, right? So this bond has some amount of energy associated with it. If we break that bond and make new bonds, well, there's a change in energy. We can measure that energy of those bonds, of those reactions, by measuring just a couple variables, and we can calculate that energy that's being transitioned in that process. Now, we can't measure in a chemical reaction, we can't measure, like, let's say this HCl and sodium hydroxide. We cannot measure these two things coming together as molecules directly, right? We don't have a device that's small enough to measure that. But we can measure how their energy affects the surroundings. And what we can do is we can measure a temperature change of the water that they're in. And from that temperature change of the water, we can back calculate it to the reaction. Okay, so this week, we're going to measure 3 different processes. Some of these are going to give off energy. Some of them are going to absorb energy from the surroundings. Things that give off energy are going to cause the surroundings to warm up. Things that absorb energy are going to cause the surroundings to cool down. It's kind of weird to think about that flow of heat. It flows from a high source to a destination. When you hold an ice cube in your hand, it feels cold, but that's actually your hand is giving energy to that ice cube and causing it to melt. Weird, right? Okay, so we have 3 of these reactions today. The way we measure these is not directly, it's kind of like our titration, where we're going to watch something else and see how that something else is affected by these reactions. So today what we're going to do is we are going to look at the heat energy of the surroundings, and this, they call it the solution, plus the calorimeter. This is the surroundings. The Q is heat. And compare it to the heat, this Q is heat of the system. And our system in this situation is going to be those chemical reactions. And so basically we can rearrange and solve for the heat of reaction. What we're going to find is the heat that's given off or absorbed by that reaction is identical in magnitude, so the number's the same, but opposite in sign. Okay? So if this reaction's giving off energy, it would be a negative Q value, and this side would be positive. The number would be the same. Okay, so we're going to measure what happens to those surroundings and back calculate it to the reaction. When we go through and measure this, usually we report this heat as something called enthalpy of a reaction. Okay, so it's this delta H reaction. And what that is just the heat of that reaction divided by the amount of moles that were in that process. It's a per mole process. Okay? So for each of these reactions, we are going to calculate how many moles went into it, or in this case, this is going to be a limiting reactant. Calculate how many moles of sodium chloride or water were produced. Or, in this case, I think we're using the magnesium to figure out, this will be limiting, how many moles went in. All right. So today, real thrilling, guys. These are our calorimeters. We don't want the energy to go into the entire room, right? Because if we don't isolate this system a little bit, the energy would flow into the entire room. And so this is actually really nice. We have really nice styrofoam insulated containers. They work pretty well. Here, this is probably the fanciest place I've ever seen. They actually went out and bought these. I guess this was a pandemic. Or just most places you just get 2 coffee cups and a woohoo, here you go. All right? So I told you it's going to be thrilling. You're going to put 2 things that look like water or something that looks like salt and water in here. You're going to put a lid on it. You're going to put some temperature probes in it, and it's going to measure the temperature. Okay? Kind of boring. Temperature change also is not going to be huge. It's not going to be like, whoa, 20 degrees. It's going to be pretty small. And we're going to do this graphically today. From that temperature change and the mass of water that's in here for our reaction medium, and from the amount of reactants we put in here, we can calculate thermodynamic quantity, so that delta H reaction. And we can compare that to what has been studied and reported in the literature. When we talk about literature, that's what a generally accepted value for that is. It's just kind of neat, right? We can just take a temperature measurement and some masses and figure this out. All right, so we're mixing this stuff in here. Now, the surroundings includes this styrofoam cup. And this styrofoam cup has the ability to take on some heat. So the first part of the experiment is to figure out how much heat this styrofoam cup can exchange. The way we're going to do that is we're going to take hot water and cold water. We're going to mix them together, and they're going to equilibrate. Okay? We're going to get the masses of those. And we're going to do this, for some reason, you could do this with a regular old thermometer, but for some reason we're using the veneer probes today. They want you to print your graphs and include the picture of your graphs. They're not real graphs. So we're going to have one temperature probe in our hot water, one temperature probe in our cold water, and those two, when we mix them together, are going to equilibrate to the same temperature. Those two lines should intersect and travel along the same path. Okay? What we can do is we can look at the energy lost from our hot water and the energy gained from our cold water and determine how much energy went into the calorimeter. Our first setup here is the heat from the hot water and the heat from cold water plus the heat of the calorimeter is equal to 0. So we can rearrange this and solve for Q calorimeter. Okay? The heat that was gained by the calorimeter. The way that we solve for the water is based on a known value. That water has the ability to take on a certain amount of energy in joules per gram of water per degree Celsius. So this is the specific heat of water, and we're going to use this constant throughout the lab. If we're solving for Q, which is an energy variable, if we're solving for joules from this hot water, we're going to look at how many grams of hot water went in here. You should measure this precisely. Don't just say 50 milliliters is equal to 50 grams. How many grams of hot water went into this, and what temperature change did that hot water experience? So for the temperature of the hot water, I'm looking that it started at a high temperature and it went to this equilibration temperature. And that'll be my delta T. So if I take my mass, where do I have it written up here? My mass of water times that specific heat of that hot water, well, it's all water, times the specific heat of water, times that change in hot water, this will give me Q hot water. For the cold water, I'm going to do the same thing. The mass might not be exactly the same. The temperature change should definitely not be exactly the same, right? Because the temperature change here, the cold water started here and went up to the middle point. Okay? I can add those together, put them on the other side of the equation, and figure out the heat that was gained by the styrofoam cup. Now, using the heat that was gained by the styrofoam cup divided by the change of the cold water, we can figure out what's called a calorimetry constant for this cup. And we can use that calorimetry constant when we do our other calculations. Okay? Because this is part of our surroundings that we're going to be measuring. All right, so that's basically the first step, and there's a lot of calculations in the first step. Each of the reactions after that are going to follow the same type of process. We are going to mix our stuff into, first I should step back a second. When you mix your two water temperatures, you want to mix hot water into cold water. And the reason for that is when you put the hot water in this, it is going to absorb some amount of heat from that hot water, and we don't want to deal with that initial heat. We want it to be based on kind of a baseline of where it was so that it equilibrates. Okay, so hot water goes into cold in that first part. I think we're done with that. Now, in our other experiments, we are measuring that energy that's given off from that substance or that reaction by measuring that temperature change of the surroundings, the water that it exists in. Okay? So we're going to need the mass of water or mass of solution that's in here. We're going to measure the temperature change of the solution, and we're going to use the specific heat of that solution. Then we can measure the heat that was gained by the solution, and we're going to add in an extra little piece for what was absorbed by the calorimeter using the calorimetry constant. And we'll be able to calculate the heat exchange. So whatever was gained by the water was going to be what was lost by our reaction. Or whatever was lost from the water is what was gained by our reaction. From there, we can calculate the number of moles that went into that reaction and determine the enthalpy of the reaction. Compare it to a literature value. When I say compare it to a literature value, you can Google this and then double check with me if you want to know the numbers. The sign of these are important because the sign is going to tell us whether the process is endothermic, absorbing heat, or if it's exothermic, giving off heat. Okay? Things that are negative delta H are giving off heat. They're warming up. Things that are positive are absorbing. Let's see. I think that's kind of it. Are you guys feeling okay with this? You're like, I don't really know what we're doing, but I'm going to follow the directions. I think the calculations are set up pretty well. In terms of measuring, we need to get masses of things at the beginning, and we're going to measure the temperature. It's going to be done graphically, so you're going to get a graph for each of these to measure that temperature. We need a delta T and the mass and the amount of stuff going in, and we can do these calculations. Does that sound okay?
You just have the liquids straight into the styrofoam, right?
The what?
The liquids or the water goes straight into the styrofoam container?
Yep, yeah. Oh, somebody turned off the water. Turn it back on. Sorry, was it too loud? I'm sorry. I'll try to talk louder. Just turn on a trickle or something because we want it hot. It takes a while for it to heat up. So you don't have to do these 2, 3, and 4 in any particular order. If people are using other reagents and you can't get in there, you can do whichever order you want for those. Part 4, I'd like for you to do in your mini fume hood if possible. It does give off some hydrogen gas. I think it's probably okay. Our EHS officer says that we should probably do it in the mini hood. I mean, it's in here and there's some gases in there too. Any other questions? There's a lot of waiting in this one. You want to get started? You know, oh, the other thing. Guys, we don't have lab next week. We don't have lab next week.